Let's go to our next speaker, Joseph from University of Bristol, our very own Bristol. We will be talking about hybridizing NV filters with nitride photonics for high efficiency sources like indistinguishable photons at 200K. Before starting, can I please ask you if you have both the backstage and the main stage? Can you please turn the audio of the main stage off? You can see a bit of a coming back noise.
I don't think I got that. Okay, thank you for the introduction. This work was funded by the British Council and by EPSRC. Firstly, I'm going to go over the results of our experimental paper with Jorge Monroy-Ruz, but spend most of my time on this new result with Chloe Clear and Dara McCutcheon. This research is managed by Krishna Balram and John Rarity. So we're interested in controlling optically accessible atom-like sources of entanglement. We want to find a route to do this at scale using the best understood systems we have, the NV center, which are isolated defects in diamond that emit single photons. The NV center has an associated electron spin that can be coherently manipulated at room temperature. In this paper from last year, we show that we can characterize a single NV center in a nanodiamond, take it out of the lab, grow silicon nitride over it, and go back to the same NV center and measure its quantum properties. We can recover the single photon statistics from the single emitter without correcting for background noise, and the extra spin bar from the silicon nitride matrix doesn't have a serious effect on its spin coherence. So the results benchmark this hybrid material of NV centers and silicon nitride as a useful platform for quantum technology. However, if we're going to do quantum photonics, it's not good enough to just have an emitter of photons. We need these photons to be coherent with one another. And the NV center isn't naturally the best system for this. This is what the photoluminescence from an NV center looks like at room temperature. There's two distinct and important parts here. Firstly, it's the breadth of this zero phonon line in orange. The NV center is connected to a diamond lattice, which firmly shakes around and causes jitter in the time at which photons are emitted, resulting in a very broad emission line. The second effect is that the diamond has vibrational modes, causing photons to be redshifted as energy is lost to these phononic modes. This results in a broad sideband shown in blue. We can put some numbers on how these two features affect the coherence of photons from the NV center. Compared to the natural emission rate of the NV center, which is 30 megahertz, the dephase rate in this emitter is 15 terahertz. And this ratio has a serious impact on the coherence of the NV emission. This is prefactored by the Debye-Waller, which is 4% squared. So together, this gives a total indistinguishability of a bare emitter of around 1 in a billion photons. So this is the problem with solid-state systems. A perfect atom in a vacuum, the photons would emerge at steady intervals. A solid-state crystal has this connected lattice of atoms. So every time I pump the NV sensor, the thermal vibrations of the lattice disturb this transition and create uncertainty or jitter as to when the photon is emitted. If I build a cavity around this NV center, I can increase the strength of the interaction between light and matter and cause the rate of photons to increase. And with the right cavity, we could force the NV center to eject photons so rapidly out into the waveguide channel, it doesn't have time to interact with its environment. Such a cavity atom system would act as a new effective jitter-free emitter. Firstly, a cavity modifies the spatial density of states set by the optical mode volume. We refer to this as the G coupling. You get a large G coupling with a tiny mode volume as the interaction between the atom and its light increases compared to free space. Cavities also modify the spectral density of states, the quality factor of the cavity. If you have a high Q, high quality factor cavity, the photon bounces back and forth against mirrors, and there's a small cavity leakage rate out of the system. We call this the kappa rate. A recent breakthrough in small mode volume cavities are these bow tie photonic crystal nanobeams. Designed by Sharon Weiss's group and first fabricated by IBM, they allow the photonic energy to be concentrated at the apex of the bow tie, as opposed to traditional photonic crystals where the mode is either confined in the air hole or the dielectric part. In this figure, we're putting the NV center dephasing and cavity parameters into a master equation model and calculating the indistinguishability of the zero phonon line in different cavities. Photonic crystal nanobeam cavities normally have mode volumes of order lambda over n cubed. For this high dephasing, shown in red, indistinguishability maxes out around 0.2, whereas the smaller mode volume, higher G coupling, can overcome the dephasing and reach indistinguishabilities towards unity in green. The interesting thing to mention is this curve isn't monotonic, so you can't get around a large mode volume with a higher Q factor. You can't just push G over kappa. This alone is one of the key reasons it's important to do careful cavity QED analyses rather than relying on a Q over V argument. Arbitrary high G without dampening with moderate Q enters into strong coupling. So for the orange line, you can see the best indistinguishability is just at the onset of strong coupling at a Q of 840. At higher Q of 1500, the emission splits into two modes and the indistinguishability drops. So for dephased emitters, it looks like this new type of bow tie geometry is able to do things that standard 1D photonic crystals can't do. However, the zero phonon line is only part of the picture. We want to include the effects of the sideband as well. Our full model calculates the two-color spectrum. So this is the Fourier transform of the correlation function. This spectral domain expression is then normalized by the power in the zero phonon line plus the power in the cavity filtered sideband to find the total system indistinguishability. Now we've captured the sideband, we can create a contour plot and look for the ideal cavity parameters for the NV center. With the sideband included in the model, we've got something else going on. So as I said before, for a highly dephased system, you want to lower that quality factor to stay out of strong coupling. However, this means that if you've got a low quality factor, you funnel a lot of the sideband emission into the cavity emission line. So for significant sideband, there's a trade-off in improving the zero phonon line dephasing and getting rid of as much of the sideband as possible. The compromise we went for is to cool a little bit. So instead of room temperature, we use a Peltier, which is an interface of two semiconductors that creates a heat gradient. Cooling to the limits of Peltier cooling, 200 Kelvin, results in an order of magnitude narrowing in the zero phonon line. So now we can afford to have a larger mode volume to overcome this dephasing. So we don't need such a small Q to stay out of the strong coupling, so we can filter away a larger chunk of the sideband. So looking at the maximum of this 200 Kelvin plot, we need a moderate Q of 1000. We want a fairly small mode volume of 1/20th lambda over m cubed. However, this is actually much larger than the 10 to the minus 4 cavities demonstrated by IBM. Using FDTD simulations, we can design this cavity in silicon nitride. We make a planar structure that can be fabricated using standard lithography with this bow tie shape confining the modal field. We're inserting a 20 nanometer nanodiamond into this silicon nitride structure to load in our NV center. Diamond has a refractive index of 2.4 compared to silicon nitride's 2, so you get modal confinement out of plane for free owing to this. Our final design, we now need to hit that Q using 5-unit cells that taper the hole in the bow tie unit cell and create a Gaussian moded defect as seen in the inset. With 5 taper pairs, we have a design that gets us over that 50% indistinguishability threshold as shown in this orange square. So compared to high Q designs, which take hundreds of microns, this cavity is very compact, only about 10 microns, so it lends itself well to high emitter density in an integrated platform. One point that's important to note with photonic crystal cavities, as opposed to, for instance, ring resonators, is the very large free spectral range. So if we plot the next energy mode of this structure, it's far outside the sideband of the NV sensor. Also, in our Masters equation model, we're saying sideband emission is left unchanged in its rate by the cavity. It's just spectrally filtered. What we might see in practice, in fact, is the sideband suppressed because it's in this forbidden band gap. So suppressed below its free space emission rate. To cover the sideband in the master equation model, we'd need a much larger Hilbert space to capture these transitions. We can say our model of sideband, as always dephased, is a lower bound on the indistinguishability. And for us, demonstrating that we can pass that 50% was the important point, bearing in mind where we were before engineering the cavity, where we expect 1 in a billion photons were useful for quantum interference. We've gone up by 9 orders of magnitude. How can we further boost this indistinguishability in our model? So this cavity regime puts the system at unit efficiency. Every time we excite the NV sensor, we get a photon into the cavity mode. What we can do is add an external filter to throw away some of these sideband photons at a loss of efficiency to the system. So we add to the indistinguishability this filter term, and we can see that the indistinguishability increases in this inset plot in blue. And we can normalize the power into this filtered mode by the unfiltered power to find the new efficiency beta in orange. And dependent on our needs, target say 75% system indistinguishability with 30% efficiency at 200 Kelvin. So here's some plots of the spectra on a log scale using the best cavity parameters of each temperature regime. If we go along the bottom for the 200 Kelvin case, as we showed before, the best place to be is just at the onset of strong coupling. We have a cavity Q that rejects a portion of the sideband. However, there's still the tails of the sideband in our emission spectra contributing distinguishable photons. We stick an external filter on the split peak furthest from the sideband to boost this number higher, but now we're filtering away some of the indistinguishable photons as well. One of the interesting studies in this paper was to look at the effects when the NV sensor is not well oriented with the cavity mode. So normally this dot product orientation would be modeled as an efficiency loss. However, the NV sensor is a bit different, and it actually has 2 optical dipoles. And at low temperature, the main dephasing mechanism is the Antella effect, dephasing between these 2 polarization levels. So in these calculations, we see how free-level system dephasing would result in a drop in the indistinguishability dependent on the dipole orientation. In warmer temperature regimes, when the dephasing is much larger, it's currently expected pure dephasing through the shelving state is actually dominant. However, there's some debate here, and we hope this type of cavity framework would allow us to distinguish the dominant dephasing mechanism experimentally. To take away, I think there's 3 useful points that have come from this work. Small mode volumes are the route to getting dephased emitters to generate indistinguishable photons. And when you have dephasing, which is most solid state emitters to a certain extent, you can't just calculate a Purcell from Q over V. You need to do a careful Masters equation analysis to include dephasing. Where sidebands are significant, you have to trade off what's best for getting coherent photons from the zero phonon line to what's best to filter from the sideband. For an in-depth look at the maths in this paper, Chloe Clear was the driving force behind the Masters equation modeling. I advertised Chloe's poster and number 7 at the BQIT poster session to find out a bit more. In terms of future work, we're now looking to test some of these cavities, or at least intermediate versions of them experimentally. So here's some pictures of nanodiamonds we positioned in different experiments. Last week we started a project with IMEC working on this. There are also some theoretical questions we want to address regarding the dominant dephasing mechanisms in this temperature regime, and whether these results can be improved by making the sideband fraction coherent under tight filtering.
Thank you very much, Joe. That was a very interesting talk and very fascinating to see these pictures of very recent work. Thank you very much. So I cannot see still any questions. Oh yeah, we have one from Alex Clark. Could you comment on whether you expect there to be surface effects from using such small nanodiamonds in these very small cavities, such as spectral wandering or surface-induced dephasing?
Yeah, no, certainly there will be. And it's interesting in Professor Ladau's talk, he was talking about these different mechanisms, and some of these effects are on different timescales that aren't so important for indistinguishability. But when they are on this timescale, then you would want to add this as a framework in your framework, and it'd be interesting to see if you could just model that as pure dephasing, or whether you'd need to add some different parameter in your model to compensate for that.
Very good, thank you very much. I cannot see more questions showing up on the chat. Maybe it's just people typing quickly around. I have one question from me, actually. How accurately can you place this, nanodiamond in the? So, do you have any control on the positioning, or you just arrange everything around them when you?
No, the positioning is deterministic. So we use templates in photolithography to position these nanodiamonds. But then you have this added thing about where is your atom within this nanodiamond. So the nanodiamond works. It's great in some sense that you have this 20 nanometer accuracy that your atom is in this position nanodiamond. But the bad thing is that is your limit. So your atom is stochastic to within that 20 nanometer, which would affect what your experimental G is, because you'd expect some fall off if it's away from the mode center.
Yeah, very, very interesting. Thanks a lot, Joe. I cannot see any more questions showing up in the Q&A, but we will make sure you receive further questions in case they come late. Thank you very much again. Let's move to our